You sit in the class.
Since the very dawn of time, our closest celestial neighbor has fascinated observers with its unfailingly predictable cycle of movement through the night sky.
It's not at all surprising that the moon has been used as a calendar device and a timekeeping device. The moon's a very obvious object in the sky, one of the most obvious, in fact, the second brightest after the sun. It also moves relatively quickly among the background stars, and its times of rising and setting change, as well as its positions of rising and setting. And all of these things happen quickly enough so that people would notice them. Well, these effects combined with the fact that the moon changes its appearance fairly quickly, too. It goes through phases in a length of time that we've subsequently called 1 month, a word which just derives from the word moon. All lead us to believe that it's quite natural that people would have first begun to measure time by using the moon. We don't really know when this began, but it is possible that it began as early as 20 to 30,000 years ago, in the time of the Old Stone Age. In these Old Stone Age times, or Paleolithic times, we find bones with notations on them that have been interpreted as a sequence of the tally of the days, just in terms of the phases of the moon, the changing appearance of the moon from day to day.
We've gained an enormous amount of knowledge about our satellite, its geology, chemistry, its structure, and its motions. But even without sophisticated instruments, just by carefully watching the night sky, anyone can learn a great deal about the moon, particularly the night-to-night shifts in the moon's position and the changes in its phase. The light from the sun always illuminates one half of the moon, and one half, or one hemisphere, of the earth. What we call moonlight is simply the light from the sun which is being reflected by the surface of the moon. And as the relative positions of the moon, the earth, and the sun change during the course of a month, we notice nightly changes in the position of the moon in the sky, the times at which it rises and sets, and the various phases of the moon. From a pale, thin crescent, to a bright, full moon, to a new moon, which we can't see at all. The cycle of the moon's phases begins with the new moon. At that point, the moon is almost directly between the earth and the sun, and we don't see it at all. A few days later, as the moon travels eastward in relation to the sun, a thin crescent appears low in the western sky just after sunset, and sets very shortly after the sun itself has set. Over the next few nights, this waxing crescent grows larger in size and appears higher in the sky after sunset, and sets later and later on the following nights. About 1 week after the new moon, the moon reaches the first quarter phase and sets about 6 hours after the sun. In the following week, as the moon continues on its orbit around the earth, it reaches the waxing gibbous phase, which means that it's more than a half moon, but not yet a full moon. Then, about 2 weeks after the new moon, it reaches the full moon phase, which means that the moon is now on the opposite side of the earth from the sun. The full moon rises as the sun is setting and remains visible throughout the entire night. As the moon continues around the earth, back toward the sun, the cycle of phases reverses itself over the next 2 weeks, shrinking from a full moon to a waning gibbous, to the last quarter a few days later, then a waning crescent, and again a new moon, as it returns to a point between the earth and the sun. The moon's orbit around the earth can be described as an ellipse of small eccentricity, which means that it's almost circular. And as the moon revolves around the Earth, it's also moving along with the Earth as we travel around the sun. It takes the moon 27 1/3 days to make one complete revolution around the Earth on its orbit. Those 27 1/3 days are called the sidereal month. But because the Earth is also moving around the sun, it takes the moon about 2 more days to return to its new moon position between the Earth and the sun. So the period in which the moon completes a full cycle of phases is actually 29.5 days, and it's called the synodic month. Just as the Earth's gravity affects the moon's gravity has a number of important effects on the Earth. To begin with, it's the gravitational pull of the moon that produces the regular tides, high tide and low tide, on the bodies of water on the Earth. The gravitational pull of the moon produces 2 tidal bulges on opposite sides of the Earth. The tidal bulge on the side closest to the moon is due to the fact that the moon's gravitation pulls harder on the water closest to it. The tidal bulge on the opposite side of the Earth is due to the fact that at this point, the moon's gravitational pull is weaker. So the water levels on this side, in a sense, drop away from the moon's pull, forming a similar bulge. If we let the tidal bulges represent high tides, then the 2 points at right angles to the bulges, which are also on opposite sides of the planet, would be experiencing low tides at that point in the Earth's rotation. And since the Earth rotates once every 24 hours, each point on the planet will experience a high tide and a low tide twice each day. The average interval between successive high and low tides is 12 hours and 25 minutes. The gravitational pull of the sun also affects the tides on Earth, but not nearly as much as the moon, because of its much greater distance from the Earth. Because the moon's orbit is slightly elliptical rather than a perfect circle, its distance from the Earth varies as it travels in its orbit. The moon's maximum distance from the Earth is called apogee. The moon's minimum distance from the Earth is called perigee. By averaging these 2 distances at apogee and perigee, we find that the mean distance of the moon from the Earth is about 384,000 kilometers, or 240,000 miles. The equatorial diameter of the moon is just over 1/4 of the Earth's equatorial diameter. Although astronomers have been able to make fairly accurate measurements of the moon's dimensions for centuries, today, using instruments left behind by the Apollo astronauts, scientists can measure the distance of the moon within an accuracy of a few centimeters. Dr. Jim Williams at Caltech's Jet Propulsion Laboratory has conducted extensive studies of the motions of the moon and is involved with the Lunar Laser Ranging Experiment.
Okay, the Lunar Laser Ranging Experiment is an experiment that's been going on now since 1969, since the first Apollo astronauts visited the moon. Now, let me explain the experiment first. What happens is there are observatories on the Earth which have high-power lasers. These high-power lasers shoot out a very intense beam of light, but it's very short. It's less than about a yard in length. Now, this light takes about a second and a quarter to get out to the moon. On the moon, there are special reflectors that have been placed down, and these have been placed down at 5 spots. They were placed down by 3 of the Apollo missions, the Apollo 11, 14, and 15 missions, and they were also placed down on 2 of the Russian vehicles, and those are French reflectors that are on the Russian vehicles. So there are 5 spots on the moon where there are reflectors, but in fact, one of those is not working right, so there's really only 4 that we can use. Now, these reflectors, called corner cube reflectors, are designed such that when a beam of light strikes them, they return the beam exactly in the opposite direction from which it came. So the beam takes a second and a quarter to go out to the moon, reflects, takes a second and a quarter to come back to the Earth again. On the Earth, there are very sensitive detectors at these same observatories. And these sensitive detectors measure the time interval was that it took to go out and come back. Now, the reason this is worthwhile doing is this time interval can be measured very accurately. It can be measured to something like a billionth of a second. better than a billionth of a second. And if you translate this into how accurately you can measure the distance, that turns out to be a few centimeters. And in fact, our best, most accurate ranges that have been made so far are about 5 centimeters in accuracy. That's about that much. And when you can get measurements that are this fine, there's a lot of things you can learn about both the Earth and the Moon. There are several observatories on the Earth which have ranged the Moon. Most of the ranging data has come from the McDonald Observatory, which is in western Texas and operated by the University of Texas. There's a second observatory which has recently started ranging the Moon, which is in Hawaii. It's on the island of Maui. It's on the volcano of Haleakala, and it's operated by the University of Hawaii. There are also ranges which have been obtained in Russia at the Crimean Astrophysical Observatory.
Dr. Viktor Abalakin is a department head at the Soviet Institute of Theoretical Astronomy in Leningrad.
In the Soviet Union, the laser ranging experiments are performed by a group of physicists from the Physical Institute named by Lebedev of Academy of Sciences of USSR under leadership of Dr. Kokurin. They have designed and constructed the laser ranging apparatus, which is working in combination with a great telescope on the Crimean Astrophysical Observatory, so-called Shine telescope, having the mirror of 2.6 meters in diameter. The precision of calculation of the lunar distances is rather high. It is of the order of several centimeters. But methodical accuracy of getting these measurements is, as I guess, is several tens of centimeters. In the future, the laser ranging experiments, their results will be used for a wide range of problems, beginning with geophysical ones. It's giving the evidence of the drift of the continents. Then we get much more information about the motion of the axis of rotation of the Earth in inertial space. And then we get information as to our knowing our stations on the surface of the Earth.
The light from the sun always illuminates one half of both the Earth and the Moon. But occasionally, the shadow of one orbiting body falls on the other, and that's called an eclipse. A total solar eclipse is one of nature's great spectacles. It occurs when the Moon moves directly in front of the sun. When that happens, an observer on Earth sees the sun completely covered by the Moon for as long as 7 minutes.
Eclipses are unusual and spectacular events. When they occur, the appearance of the sun or the moon changes dramatically, and that, of course, also can cause concern, particularly for people who aren't familiar with exactly what's going on. We know that in ancient times, people did have that kind of concern about either of those two most familiar objects in the sky, and so as a result, they tried to deal with eclipses as well. In one case, we know that people imagined an eclipse as actually a dragon that was taking a bite to devour the sun. They had a remedy for this problem, however. When the dragon began making his dinner out of the sun, the people would march out into the streets with pots and pans and make a loud din and noise in an attempt to chase away the dragon. Well, the method was remarkably effective. Every time it was employed, sure enough, the dragon left and the sun returned to normal. We know people also tried to predict eclipses in ancient times. The ancient Babylonians did this very thing. They weren't always accurate, however. In fact, there were times when they predicted eclipses which didn't occur. They didn't blame that on the astronomers, however. When that happened, they just figured that something odd was happening in the sky, and that was probably the king's fault. And so he was required to do penance for it.
A solar eclipse is the result of a number of factors. Although the difference in size is much greater than shown here, the sun is nearly 400 times as large as the moon. But since the sun is also nearly 400 times farther away than the moon, to an observer on the Earth, the sun and the moon have the same angular diameter. Another factor in the phenomenon of a solar eclipse is the shadow cast by the moon, an inner cone of dense shadow, the umbra, and a surrounding region of partial shadow, the penumbra. When a solar eclipse is seen from the region of the Earth covered by the penumbra, only a part of the sun's disk is hidden by the moon, and that's called a partial eclipse of the sun. But when seen from the very small area covered by the dense shadow of the umbra, the sun is completely blocked out by the moon, and that's a total eclipse of the sun. A third type, called an annular eclipse, occurs when the moon doesn't appear large enough to completely block out the sun. In that case, the bright solar disk can still be seen as a dazzling ring around the moon. In fact, annular is a derivative of the Latin word annulus, which means ring.
There are at least 2 times each year when it's impossible for the moon's shadow to miss falling on the Earth. But it only strikes the very surface of the Earth along a thin line that moves across the Earth while the Earth turns and while the moon moves in its orbit. A line we call the eclipse path. Now, to see the sun covered by the moon, you must be in that very special place on the Earth where the very tip of the moon's shadow strikes the surface of the Earth. It only takes a very few minutes for the tip of the shadow to pass by a particular place on the Earth, so an eclipse of the sun can only last for a few minutes. In fact, at most, about 7 minutes. It can happen as many as 5 times a year under optimum circumstances, but it must happen at least twice a year. But very few people have seen total eclipses of the sun because it's only along that thin line. The American Ephemeris, the almanac published by the U.S. Naval Observatory, always lists the eclipses that are going to occur during a given year, and in the ephemeris you'll find maps that show where these eclipse paths move across the surface of the Earth. Here, for example, is a map that shows the circumstances of the famous eclipse back in 1973. And you can investigate these maps and find the very small path across the Earth where the eclipse can be seen. We know for many years in advance, in fact for hundreds of years, where these eclipse paths will strike the ground, so it's possible to plan a long way ahead. And people who study the sun, who are interested in the conditions of the lower atmosphere of the sun, the chromosphere, and the inner corona, prepare their experiments for years in advance and arrange to go to the right place on the Earth where they can witness this very spectacular event. I've been very lucky, I should say, to have been on 5 such eclipse trips myself. But I'm not a solar astronomer, and I was always along to make popular lectures. It is a very exciting and moving experience, I can assure you.
Even when the moon's umbra reaches the Earth, it usually covers an area no more than 60 miles across and sweeps along at more than 1,500 miles per hour, passing the observers on the ground in less than 7 minutes. Often, a jet aircraft is used to extend the observations by racing along with the eclipse shadow. But on the ground, only those observers in the narrow path of the fast-moving umbra can witness this spectacle of a total eclipse of the sun. During this eclipse, the clouds begin to darken and a soft twilight spreads across the land, announcing the approach of totality. Through the telescope, this is the fleeting moment which these scientists have traveled so far to witness. A closer examination of those few minutes will reveal the anatomy of a solar eclipse. Just before totality, we see only a thin crescent of the sun's chromosphere, the gaseous atmosphere that envelops the sun. The spots at the sun's opposite edge are called prominences. They are actually bright glowing regions of the sun's atmosphere, which resemble long, flame-like tongues. The prominences extend as far as 250,000 miles outward from the sun, and eruptive ones have been known to move at speeds as fast as 250 miles per second. The eclipse proceeds to totality. Now the sun is completely covered by the moon, allowing us to see the faint pearly glow of another gaseous layer surrounding the sun and its chromosphere. This outer layer is called the corona. The gases of the corona are thin, and they reflect and scatter light to produce the halo effect. In this view, The clouds in the Earth's atmosphere obscure the full extent of the corona. But as the clouds pass, the full corona appears, extending more than 500,000 miles outward from the sun. This is the prime target of most eclipse expeditions. Its temperature is almost 1,000,000 degrees, and data recorded from it gives scientists a unique opportunity to study characteristics of high temperature gas.
One of the most spectacular solar eclipses that I saw was my first one. It was in 1970 in March, and we saw it in Mexico. We were in the middle of a beautiful desert on a knob of a hill. The desert was all around us, perfectly clear sky.
March 6th, the day before the eclipse. Despite a cloudy sky and a pall of smoke from a nearby brush fire, the observing team runs through a full dress rehearsal. 6 highly specialized experiments, 24 solar observers, and over a year of planning, traveling, calibrating, and most of all, waiting. Waiting and hoping for a clear day for tomorrow's eclipse. March 7th, 1970. The dawn reveals a brilliant crystal clear sky. And better yet, a good luck breeze forces the smoke from the brush fire away from the camp. The astronomers knew that this day was theirs. The Mexican government has been extremely cooperative, and they've assigned a special detachment of troops to intercept sightseeing visitors and traffic. 10:08 a.m. The moon makes its first contact with the sun's disk. Totality is 1.5 hours away. Acting as tiny pinhole cameras, the spaces between the foliage cast remarkable images of the solar crescent.
The excitement was just electric. And as the hour drew nearer, you began to see a little bite out of the sun where the moon began to cover the sun's disk in the sky, about an hour before totality. Well, the first 3/4 of an hour, not much happens, except you can see more and more of the sun covered. Of course, you take care not to look at it directly, but through special filters. But gradually, as the eclipse gets almost total, you feel the air getting cooler. Breezes come up. And off to one side, you can see the sky looks much darker than the other. And you can actually see the shadow of the moon hanging out of the sky like a great kind of fuzzy curtain. And you can see it sweeping across the desert as the shadow rushes toward us. And the temperature dropped on that eclipse more than 10 degrees. Breezes came up. The excitement just built up more and more. In the last few seconds, it was almost as if someone were turning a rheostat down, so suddenly did the sky get dark.
Prepare for manual film advance. Manual film advance mark. Manual film advance.
And then, just in the instant as the moon covered up the entire disk of the sun, you begin to see a few little bright red beads around the advancing limb of the moon, the so-called Bailey's beads, where the last rays of the sun are shining through the low valleys on the moon. And then finally, as the sun's just about covered, the last of these beads becomes the diamond ring, a big last flash of sunlight. It looks almost like a diamond surrounded by a bright ring, because now the moon has covered up the bright part of the sun, and you see light coming from the inner corona, the inner part of the sun's atmosphere.
5, 4, 3, 2, 1. Now, new course. One standby.
As the diamond ring died out, the whole place just fell in awe. You could see the brighter stars and the planets in the sky. Bats actually began flying about. The Mexicans were just, everyone was shouting the same thing. I can't believe it, it's fantastic. And applause broke out, actual applause. And it lasted for about 3 minutes. And at the end, the whole thing goes through in reverse order. It's something bigger than man. It's something happening in nature that man himself can't reproduce.
In the span of just 3 minutes, the eclipse team has gained enough data to support months of analysis and research. A solar eclipse occurs when the moon is between the Earth and the sun, the new moon phase. When the moon is on the opposite side of the Earth, at the full moon phase, the Earth occasionally blocks out the sun from the moon's viewpoint, just as the new moon blocks out the sun from our viewpoint during a solar eclipse. So, a lunar eclipse occurs when the moon, as it orbits around the Earth, falls into the Earth's shadow. In this sequence, through an observatory telescope, the moon is entering the Earth's umbra. It takes the moon about 2 hours to pass through the dense shadow area of the Earth's umbra. And in that time, the moon will travel about 5,000 miles in its orbit. The moon orbits around the Earth about every 27 days, but eclipses of the sun and the moon don't occur every month, because the moon usually moves above or below the imaginary line between the sun and the Earth.
Well, of course, there are solar eclipses and lunar eclipses, but there are also stellar eclipses, eclipses of stars, and they're actually called occultations. The most familiar kind of an occultation is a lunar occultation, and it occurs simply when the disk of the moon crosses in front of a star and blocks out its light for a period of time. Planets can do this as well, and these occultations of stars by the moon or planets can be predicted. And in fact, one such occultation of a star by the planet Uranus ultimately resulted in the discovery of a set of rings around the planet Uranus.
There was a time when an eclipse was one of the most awesome and terrifying events imaginable. Today, for the astronomer, an eclipse can be an invaluable opportunity for research. And for those fortunate few who can witness a total solar eclipse, it's an opportunity that may come once in a lifetime.
Variation on top of that, but... 5, 4, 3, 2, 1, mark. I see a Newkirk, dark slide in. Okay.